Okay, so we're now going to apply what we had last time in terms of Kepler's third law and apply it to actually real systems to try and derive masses of stars. Okay, and we're going to split that up into two types of binary systems, which we're going to define now. So, an obvious type of a binary system is what we would call a visual binary. Okay, and this is where you can, when you take an image, you can actually see two stars clearly separated. So again, going back to our sort of workshop one on spatial resolution, if you can actually spatially resolve the two stars, then that's a good start. But of course, you might have two stars like this that just happen to line up on the sky and are not actually anything to do with each other, not in a binary system. If that's the case, it's referred to as just a double star, so they just happen to be along the line of sight. So to prove that two stars close together on the sky like this are actually in a binary system, you have to see them orbit around each other, around their common center of mass. So you have to take multiple images over time to show that they are moving around each other in orbit. Okay? So if you do that, then that's a visual binary system. But there's a second type of binary system where we only see one star if we take an image, so we don't have enough spatial resolution to resolve the two stars. But we can use spectroscopy to prove that there are two stars there, even though we only see the one image, because of changes in the spectrum of the spectra of each star. So you get a joint spectrum of both stars, and as we shall see, you get periodic shifts in the wavelengths of their spectral lines due to the Doppler effect because of the stars orbiting each other. Okay, so we're going to deal with each of those two. So let's deal with the visual binaries first, because they're the ones that are the most sort of well constrained and give us really accurate information. So if we can watch two stars orbiting around each other, then if we wait long enough, we can measure the period. Okay, and we can also measure the separation, A, between the stars. So normally, of course, you've got the angular separation, as we saw on that previous little image there. Now, if you want to translate into the actual physical separation, of course, you do need to know the distance to the system, D. So you would have to measure the parallax to the system as well. Okay, but that can all be done, especially for nearby systems. And basically, most known visual binaries are reasonably nearby in order to get A big enough to separate the two stars. But there's another factor here that, of course, if you've got a very wide separation of the two stars, then Kepler's law also tells us that the period is very long. So if your stars are a long way apart, then their periods could be thousands of years, and therefore we're not going to be able to actually sort of measure the period, because we're not going to see them move enough to measure the period. But so for ones that are reasonably close by in distance, then we can do this. Okay, and obviously, if you've got P and A, you can easily measure the sum of the masses from Kepler's law, as we derived last time. What about the mass ratio? Well, you can do that as well. If you accurately look at the motion of the two stars, you can work out where the center of mass is as well. So then you've got the ratio of their actual orbital radii, as well as the actual separation between the two stars. You can work out where the center of mass is. And as we saw last time, then that will give us the mass ratio. So again, you normally just measure the angle from one star to the center of mass, and then from the second star to the center of mass, arcseconds there. But again, they're both at the same distance, so that ratio will be the same as the physical ratio, and that's inversely proportional to the mass ratio due to the way the center of mass works. Okay. So you've then got two equations with two unknowns, m1 and m2. So as I'm sure you know, then that means you can solve for both m1 and m2 individually. So these are the gold standard systems, really, the visual binary systems. They will give you accurate masses for both stars. Okay. So a few lectures ago, when I introduced this idea of the mass-luminosity relationship for main sequence stars, okay, remember L going as m to the 3.3, the masses going into that relationship were all measured from visual binary systems, where you know the masses accurately. Okay. But it's also why there aren't that many data points on that plot, because these are fairly rare still, because you need them to be nearby to do it. So a couple of examples here of often what the sort of data on these systems look like. So often it'll be presented like this. So you keep, even though obviously both stars are moving around the center of mass, in order to present the data, then they will fix one star and look at the orbit of the other one going around it. Okay, so the primary star, often the brighter one, and then the fainter companion star going around here. So each of these data points would be the position of the companion star at a different time as it goes round and round the orbit. So you can see in here that this one's been all the way around. Okay, and here's another example where you can see the orbit here. Again, it's elliptical, not circular. And you can see the kind of timescales involved here. So this is projecting the orbit into the future. And so the orbit of this one is, whatever it is, about 60 years by the looks of it. Okay. And that's fairly typical. But again, you can see the scale on this one. This is only 1 arc-second apart. Okay. So that's what I mean by this being hard to do again. So you need high resolution in order to resolve the two stars. Okay. And you need to wait a reasonable amount of time before you can track out the orbit. So these are all sort of bright naked eye stars, really. So there is a little complication because again we introduced last time this idea that the orbital plane will be inclined at some angle to the our line of sight. And so if I just go back for a moment, so when you see an orbit like this, it's not necessarily the true ellipse of the orbit, okay, because you're seeing it at some inclined angle. So there's a lot of details involved in sort of deprojecting that. I'm not going to go into the details, and I wouldn't recommend you did either. Just suffice to say that there's only one unique fit to data points where you can fit it with a true ellipse, but also the primary star is then at the right position of the focus of that ellipse. So if it's inclined at some angle, the sort of apparent focus of that ellipse is not where the primary star is. So basically you keep changing the inclination angle until you get that to agree, and then you know the inclination of the orbit, and you can then sort of deproject the true elliptical path of both stars. Okay, but again, I will only ever give you the deprojected values. So here's another example, coming back to our sort of another famous star we're getting to know quite well now, Sirius. So as I showed you last time, Sirius is a double star, it's binary system in itself, Sirius A and Sirius B. Okay, and here you can actually see the path of these two stars. You've got Sirius A here and Sirius B here. You can see the path of those stars over the last 100 years or so. Okay, so again, the period is about 50 years, I think. Well, I know it is. And so you can see the stars wiggling around as they orbit each other. And you can see that you've got this line C here, which is the center of mass of the system. Okay. And so I'm sure you now are familiar with this from workshop 2. So the reason for this being sort of played out across the sky like this is because Sirius also has proper motion. Okay, so the center of mass of the system is moving relative to the sun in this direction. So that's indicated here on this inset. And so if you take out the proper motion, okay, so you can work out the proper motion, you can then just see what the elliptical orbits are doing. And so it's each of these ellipses is then dragged out across the sky, and that's what gives you the path here. Okay, so that's what a visual binary would look like. And of course, on top of all of that, you've also got the parallax as well. So each year, each of these stars is also wiggling to and fro due to the parallax motion as well. Okay, which is about a quarter of an arc second, I think, something like that. No, maybe a bit more, third of an arc second. Okay, so it's so the motions are getting quite complex now. So you've got parallax motion, proper motion, and binary motion here. Okay, but that's the kind of data that goes into these mass measurements from visual binary systems. Okay, so why don't you, in the break, put this into practice yourself. So I'm giving you the data for the Sirius system. So again, once you deproject those elliptical orbits there, you find that the semi-major axis of the orbits of Sirius A and B are 2.5 arc seconds and 5 arc seconds, respectively. Okay, the period is 50 years, and the distance is 2.6 parsecs. Okay. So you should be able to put all that together from what I was just saying earlier to work out the masses of Sirius A and Sirius B, and if you can put them in solar masses again to give you some context as to whether you think you've got the right answers or not. Okay, so if you have a go at that, and see you after the break.